have a person on a ladder. Couple details. The wall that the ladder is resting against is frictionless, but it's still going to exert a normal force. The ground down here is not frictionless, so it's going to exert a normal force and it's going to exert a friction force. What we're trying to find are those horizontal and vertical forces that the ground exerts. And the horizontal force is friction, the vertical force is normal. I'm just calling them horizontal and vertical for now. It really doesn't matter exactly what we call them. And then we're going to find the normal force from the wall. So there's three things that we're trying to calculate. So as always, when you have sort of an elongated object like a ladder where forces are acting, you can't draw a point for your free body diagram. You have to draw an actual representation of that elongated object, and you have to draw the forces where they're being applied. So as mentioned, there's a vertical force that the ground exerts. I'm going to call that FV. There's a horizontal force that the ground exerts. I'm going to call that FH. Again, maybe you're not sure whether it points left or right. If you guess wrong, then you're just going to get a negative answer for your final answer for that value. The ladder itself has weight. I'm going to draw that coming from the center of mass. And that is going to be 25 times 9.8, which is 245 newtons. And then we have a person up here who also has weight, and that's going to be 75 times 9.8, which is 735 newtons. Finally, we have the wall pushing outward. I'm going to call that Fn for normal force. Of course, angles are important here. We're given that this angle right here is 60 degrees. That means that this is going to be the complement of that, which is 30 degrees. Also, this angle is the complement of that. So this is 30 here as well, and that's the same angle there, so that's 30. And then this 60 here and this angle right here are what you call alternate interior angles, which are the same. So you have to remember a little bit of geometry sometimes with these pictures in order to get the proper angles. So now, of course, we're going to add up the torques. And we want them to equal 0 so that this thing isn't moving. And as I've said before, if it's not rotating, then the torques add up to 0 around any point on this object. So we could really put an imaginary fulcrum anywhere we want to, and we should find that the torques add up to 0. However, it's going to be best for the simplicity of the math to put the fulcrum down there because it's going to cancel out these two unknowns. So let's start the process of adding up these torques. Remember, torque equals R F sine theta, and we have to take direction into account as well. Again, traditionally, the counterclockwise direction is considered positive, and the clockwise direction is considered negative. So let's go with that. So first of all, if we start at the fulcrum and we think about the torque due to the horizontal force and the vertical force, those are both 0, and the reason is the R at which both of those forces act is 0. R is the distance between the point of rotation and the point where the force is being applied. There is no distance between those 2 points. They're the same point for the horizontal force and the vertical force. So they exert no torque because they have no radius, and that's exactly why we put the fulcrum there, so it would cancel out two unknown variables. So I'm not even going to write that down. I'm going to just move along until I get to this torque here, and that is at a radius, since it's the center of mass of the ladder, that radius is L over 2. That force is 245, and the angle between the radius and the force is 30 degrees. So I'm going to do sine of 30 here. Now, if you think about which way it would make the ladder rotate, if the ladder is hinged here, this would make the ladder rotate that way. And that is the counterclockwise direction, traditionally considered the positive direction. Moving along, we get to this force right here. That would also tend to make it rotate counterclockwise. So that's also going to be positive. That is the person, and right here it says the person is 3/4 of the way up the ladder. So the distance is 3L over 4. The force is 735, and the angle is, again, 30 degrees. Moving along the ladder, finally, we get to the end of the ladder. Now, this normal force would tend to make the ladder rotate this way, which is clockwise, considered the negative direction traditionally. That distance is the full L. The force is the unknown Fn, and we have sine of 60. And so those are two torques here. Actually, these two forces exert no torque. And then we have these three, 1, 2, 3. They need to add up to 0. So now it's a matter of doing the algebra. The L's cancel out. And let me get my calculator and see what we end up with. So 245 divided by 2 times the sine of 30, and 735 times 3 divided by 4 times the sine of 30. And then add those together, and that should be equal to the normal force. So I get an answer for normal force of 336.875 newtons. And that's how much force the wall is exerting. Now we have to find the other two forces as well, the horizontal and vertical forces exerted by the ground. Here it's going to be easier if we take a look at purely forces and not torques. Remember, if something is at rest, both the torques have to add up to 0 and the forces as well. So for example, let's add up the forces in the y direction. They have to be equal to 0. And when we look at the diagram, there are 3 of them. There's negative 735, negative 245, and positive FV. Now notice here that I'm not thinking at all about clockwise versus counterclockwise. That's only for torques. When you're dealing with forces, you're thinking about, at least in the y direction, up is positive, down is negative. So the vertical force is just those two things added together, 735 and 245, which gives me 980 newtons is the total vertical force exerted by the ground. Now let's add up the forces in the x direction, and there's only 2 of them. There's positive Fn because it points to the right, and negative Fh because it points to the left. And actually we learned that Fn is 336.875. So Fn equals Fh equals 336.875. And that finishes the problem.